DC to AC inverters are used in applications where the only source available is a fixed DC source and the system requires an AC load. Some applications of these inverters include aircraft power supplies, variable speed AC motor drives, and uninterrupted power sources. Inverter circuits are commonly used to deliver power from a DC source to a commonly active AC load, employing, for example, gate-driven semiconductor devices such as MOSFETs, due to their increased switching speed and power capabilities coupled with control techniques. From these circuits, we can obtain a square wave like this. The harmonics that are present in the inverter's output voltage are high for many practical applications because they can excite a mechanical resonance, causing the load to emit acoustic noise, and especially for applications where the output voltage needs to be near sinusoidal. Electric low-pass filters are normally added at the output to remove third and higher harmonics. The design of such filters tended to be challenging when the third and fifth harmonics close to the fundamental are high. In most cases, effective filters require large size and high number of capacitive and inductive components, resulting in bulkiness. We can eliminate certain harmonics on the circuit design using pulse width modulation. This will allow us to use a simple filter to cancel the remaining harmonics. For this, we will need to have an angle, and we will determine its size later on. First, we have to obtain the Fourier series of our square wave signal produced by our output voltage, which is V of t equals to A naught plus the sum from n equals 1 to infinity of A n times cosine of omega t plus the sum from n equals 1 to infinity of Bn times sine of omega t. Obtaining the Fourier coefficients for our signal, we have that the average value is equal to 0 because the positive and negative parts of the signal cancel each other. As this signal is odd, An will be equal to 0 and Bn will be equal to 1 over the signal period times the integral from 0 to the period of the signal of V of t times sine of n omega t d omega t. Solving the integral, we have as a result of Bn 4 times V maximum over pi times n times minus cosine of n omega t from 0 to p over 2. And finally, we have that Vn is equal to 4 times V maximum over Pn times cosine of n times alpha. This equation here describes the nth harmonic for our signal. Now, as we want to have this nth harmonic equal to 0, and we want to find out the value for alpha, we solve this equation for alpha and substitute the n for a number, let's say 3. And we will now have the value for alpha that will create a signal with the third harmonic equal to 0. We can do the same for the fifth, the seventh, and so on. But with this method, we can eliminate one harmonic at a time. If we want to eliminate two harmonics, we will need two angles. This time, we will call them alpha 1 and alpha 2. Now, our Vn will be given by the next equation, which is equal to 4 times V maximum over pi times the integral from 0 to alpha 1 of B of t times sine of omega t d omega t plus the integral from alpha 1 to alpha 2 of V of t times sine of n omega t d omega t. Solving the integrals, we have that Vn is equal to 4 times V maximum over pi times n times 1 minus cosine of n alpha 1 plus cosine of n alpha 2. Now, this equation describes the nth harmonic for our signal. But if we want to eliminate 3 harmonics, we will need another angle. Repeating the same steps we did before, our Vn will be equal to this equation. In fact, we can eliminate as much harmonics as we need. In fact, to eliminate a k number of harmonics, we will need a k number of angles, having now our equation equal to this: 4 times Vm over pi n times 1 plus the sum from k equals 1 to m of minus 1 to the power of k times cosine of n alpha k. Going back to eliminating two harmonics, what we have to do now is to create a system of equations, substitute n for the number of harmonic that we wish to cancel, and equal both equations to 0. Once we solve this equation system, using computational algorithms with MATLAB, for example, we'll find the values for the angles, and we'll produce a signal with the cancellation of the harmonics we choose before. On this case, the third and fifth harmonics were eliminated, as they were the most significant ones. Now, we have obtained so far the values for the angles to give our pulse width modulation technique to create the signal for our inverter circuit and have a cheap and easy to design low pass filter. We have our output signal near as sinusoidal as possible. Thank you so much for watching.